Welcome everyone to part 1 of this playlist about the best methods for converting carboxylic esters into ketones. Esters are not the most convenient starting materials to prepare ketones, because many things can go wrong in these reactions. Anyway, certain esters can in fact be converted into ketones in high yield, and there are several strategies to suppress some of the many potential side reactions. In this first video, I'll show you some examples of the use of polar organometallic reagents as nucleophiles, mostly organolithium and organomagnesium reagents. Part 2 is about Claisen and related condensations, based on the use of ionic enolates, that is sodium, lithium and other related enolates as nucleophiles. The reagents presented in part 1 and 2 are strongly basic, what imposes certain structural limitations on the starting materials. In part 3, we'll have a look at the preparation of ketones from esters under acidic conditions that may be applicable to the preparation of base-sensitive ketones. When polar organometallics add to carbonyl groups, the electrophilicity of the carbonyl group is first enhanced by coordination to the metal. Then the nucleophilic addition of the alkyl or aryl group occurs, followed by elimination of the metal alkoxide. Unfortunately, most ketones are more electrophilic than esters, and the most critical side reaction is the addition of a second equivalent of organometallic reagent to the ketone. If this reaction is faster than the formation of the ketone, then the main product of this reaction will be a tertiary alcohol. This second addition may not occur if the initially formed metallated hemiacetal is sufficiently stable, or if the resulting ketone is quickly deprotonated, either because it is strongly acidic, or because the nucleophile is a strong base, or the reaction is conducted in the presence of strong bases. Further potential side reactions include the deprotonation of the starting ester and the alkylation of the nucleophile by the ester. Such alkylations may happen with sterically demanding esters or with allylic or benzylic esters, in particular in the presence of catalytic amounts of transition metals. The formation of tertiary alcohols can be prevented by stabilization of the initially formed hemiacetal. Esters of alpha-alkoxy or alpha-amino acids often give high yields of ketones because chelate formation stabilizes the metallated hemiacetal. Alternative strategies include silylation or complexation with boron trifluoride. If a strong base, such as LDA, is added to the reaction mixture, the target ketone may be deprotonated and thereby protected from the nucleophile. This will work best if the starting ester cannot be metallated. If the starting ester is a strong electrophile, initial addition of the nucleophile may be faster than addition to the ketone, what should also help to suppress the formation of tertiary alcohols. And ketones with electron withdrawing groups, such as trihalomethyl ketones, in general form rather stable hemiacetals that do not readily release the alcohol. The most common strategy for avoiding alcohol formation, though, is not to use an ester as electrophile, but some other carboxylic acid derivative, for instance carboxylate salts, amides, nitriles, anhydrides, or acyl halides. In my channel, you can find playlists about some of these alternative routes to prepare ketones. Let's now check some specific examples. The addition of organolithium compounds to simple esters yields mostly tertiary alcohols, even at low temperature. In this example, the reaction was run at -100 degrees Celsius and in the presence of an excess of chlorotrimethylsilane. After hydrolysis, a high yield of ketone was obtained, along with 16% of tertiary alcohol. Without chlorotrimethylsilane, the selectivity was much lower. Cooling to -100 degrees Celsius is not as easy as cooling to -78 degrees Celsius with dry ice. Liquid nitrogen is usually used in combination with a hexane or THF bath, but most solvents freeze at -100 degrees Celsius and solubilities also drop a lot. In this example, the intermediate hemiacetal was complexed with an excess of boron trifluoride etherate. This enabled the direct preparation of an alkenyl ketone from a lithiated terminal alkyne and ethyl propionate. Such alkenyl ketones are good Michael acceptors and therefore particularly difficult to prepare. Acrylates, such as the starting material of this example, are also good Michael acceptors and may react with nucleophiles at the olefinic methylene group. The main product upon reaction with phenyllithium was the phenyl ketone in this case, but 17% of tertiary alcohol was also formed. Alpha haloesters may react with carbon nucleophiles either as alkylating or acylating reagents. In this example, lithiated pyridine was mostly acylated by ethyl chloropropionate when the reaction was performed at low temperature. Similarly, treatment of ethyl bromo difluoroacetate with a slight excess of a Grignard reagent at -78 degrees Celsius gave a good yield of ketone. The electrophile here was also an electrophilic brominating reagent, but addition to the carbonyl group was a faster reaction. This example is similar to the previous one. Although methyl bromoacetate and alpha bromoketones are powerful alkylating reagents, a reasonable yield of bromoketone was obtained. Acyl acetals, such as the starting materials of these two examples, should yield more stable metallated hemiacetals upon reaction with polar organometallics. The results obtained with Grignard reagents seem to support this assumption. Nevertheless, this strategy is hardly ever used to prepare ketones. Esters of 2-methoxyethanol or 2-dimethylaminoethanol may also show a similar reactivity and be slightly better suited for the preparation of ketones than methyl or ethyl esters. Like alpha haloesters, also lactones are more reactive than non-cyclic esters and give therefore higher yields of ketones upon reaction with polar organometallics. In this example, a reactive vinyl ketone was prepared by addition of vinyl magnesium bromide to a delta lactone. In the absence of traces of copper or other late transition metals and at low temperature, polar organometallics will usually not undergo Michael additions to acrylates. Here, an alpha-methylene lactone yielded mostly a ketone upon reaction with methyl lithium at -50 degrees Celsius. A small amount of tertiary alcohol was also formed. At higher temperature, though, the selectivity of nucleophilic additions to acrylates drops. In this example, a large excess of phenyl magnesium bromide was added to an alpha-beta unsaturated ester, and extensive Michael addition occurred. Interestingly, no tertiary alcohol was formed, maybe because the ketone was sterically too crowded. Esters with an alpha heteroatom can also yield more stable metallated hemiacetals when treated with organolithium or magnesium reagents. Then, strong bases can protect the newly formed ketone by enolate formation. Although alkylamines are not sufficiently basic to deprotonate ketones stoichiometrically, a large excess of trialkylamines can sometimes suppress the formation of tertiary alcohols, maybe by lowering the Lewis acidity and thereby the reactivity of the organomagnesium compound. Here, despite the excess of Grignard reagent, a high yield of methyl ketone was obtained when the reaction was conducted in a mixture of triethylamine, THF and toluene. When butyl magnesium bromide was used as nucleophile, though, a substantial fraction of ketone was reduced to the secondary alcohol. Grignard reagents with beta hydrogen are good hydride donors and tend to yield this type of byproduct. Unfortunately, these conditions were not successful with enolizable esters such as the starting material of the third example on this slide. Here, the conversion was low, what indicates that the Grignard reagent mainly acted as base and not as nucleophile. If instead of triethylamine stronger bases are used, stoichiometric enolate formation should be possible and prevent the formation of tertiary alcohols. This strategy can of course only be applied to base-resistant non-enolizable esters. In this example, such a non-enolizable ester was treated with a slight excess of allyl magnesium chloride in the presence of LDA and lithium diethylamide at room temperature. A high yield of ketone and only small amounts of tertiary alcohol resulted. Without bases, the tertiary alcohol was the main product. Instead of using lithium bases, it may also be possible to just add secondary amines to the ester or to an excess of the polar organometallic reagent, because deprotonation of amines by these reagents is often quite fast. Carbanion-like intermediates sometimes result upon treatment of silanes with fluoride. In this example, a catalytic amount of cesium fluoride was sufficient to bring about the addition of a trifluoromethyl anion to methyl metacrylate. After hydrolysis of the initially formed silylated hemiacetal, the trifluoromethyl ketone was obtained in high yield. The addition of methylated sulfones, nitriles or ketones to esters is similar to the Claisen condensation. The products are strongly CH acidic and will be immediately deprotonated by the nucleophile. The resulting enolates react only slowly with nucleophiles, and high yields of ketone are usually obtained. An excess of nucleophile will often be required, however. In this example, a threefold excess of methylated sulfone was added to methyl benzoate, and after stirring at 80 degrees Celsius for 2 hours, a high yield of ketone resulted. This ketosulfone was highly acidic and did not even react with an excess of ethyl magnesium bromide. Like the ketosulfone of the previous example, also beta-ketoesters and 1,3-diketones are acidic and their enolate salts resistant to nucleophilic attack. In this example, the authors succeeded though in converting the sodium salt of a beta-ketoester into a 1,3-diketone by treatment with an excess of methyl lithium. Almost no alcohols were formed. Esters with alpha heteroatoms often give high yields of ketones upon reaction with polar organometallics. In this example, a serine-derived methyl ester was treated with a large excess of allylic Grignard reagent at low temperature. Allylic inversion, but no beta elimination of the silyloxy group occurred, and a high yield of the target ketone was obtained. Unlike the previous starting material, in this example the amino ester was protected at nitrogen. Despite the excess of nucleophile, neither deprotection of the amino group nor twofold addition to the ester occurred, and a quantitative yield of protected amino ketone resulted. So, what kind of side reactions are to be expected? The most prominent is, of course, the formation of tertiary alcohols, as already discussed at length. Enolysable esters may also just be deprotonated by a given polar organometallic reagent, in particular if this reagent is sterically demanding. As discussed in one previous example, tertiary or secondary amines can also cause enolate formation. Such ester enolates are not stable and will undergo Claisen condensation, notably at a high concentration and temperature. Organometallic reagents with beta hydrogen often act as hydride donors and reduce ketones to secondary alcohols, as in this example. Such reductions may also proceed by single electron transfer, as during the formation of pinacols from ketones and some metals. Some ketones form surprisingly stable hemiacetals or hydrates. The example here was not particularly stable and yielded the ketone during chromatography. But hemiacetals of some trifluoromethyl ketones or similarly electron-deficient ketones require forcing conditions to release the alcohol. Carboxylic esters may also act as alkylating reagents, in particular benzylic, allylic or methyl esters. Traces of transition metals will usually exacerbate this problem. In this example, a sterically crowded Grignard reagent was mostly allylated by allyl benzoate, without the addition of any catalyst. Polar organometallics can also add to the electron-deficient CC double bond of enones or alpha-beta unsaturated esters, even without any late transition metal catalyst. Here, for instance, the initially formed enone reacted as Michael acceptor and gave 18% of butenyl ketone. The chelate forming ability of the starting ester and low reaction temperature did not help to prevent neither the Michael addition nor the formation of a tertiary alcohol. Interestingly, some 2-alkoxybenzoates react preferentially as Michael acceptors and undergo extensive aromatic nucleophilic substitution, as in this example. Although only one equivalent of methyl magnesium iodide was added to the ester at low temperature, no ketone, but mostly a methyl arene was obtained, along with some tertiary alcohol and a phenol. On this and the next slide there are some further, mostly recent examples. You can also find this reference list in the description of this video. The next presentation of this playlist is about the use of ionic enolates as nucleophiles for the conversion of esters into ketones. This includes the important Claisen condensation. With ionic enolates, the products are always enolate salts, and the formation of tertiary alcohols is therefore less of a problem. See you then.